The solar system became small when we discovered the first world orbiting other stars. After the first discovery, a deluge of planets was gradually found around stars throughout the Milky Way, and today we have more than 5,000 worlds uncovered. However, all these planets are in fact located solely within our galaxy, and seemingly none other has been found beyond it. This is due to the implications surrounding the quest for extragalactic worlds, which is one of the most challenging tasks in planetary astronomy. However, a potential world was found 28 million light-years away from here. This could potentially be the first extragalactic planet. Welcome to Futuristic Findings, and in today's video we'll get to know M51-ULS-1B, the possibly first planet beyond the Milky Way. Discovering exoplanets has demonstrated that the likelihood of us being alone in the universe is exceedingly low. Even though we don't know the exact total variables that would allow life to reach the stage where we are on Earth today, the fact that we have an immense number of planets scattered throughout the Milky Way can be inspiring. And who knows, one day we might stumble upon a world that had the ability to foster life. In fact, we've already found many worlds in the so-called habitable zone, which in theory would give a planet the chance to support liquid water on its surface. But the truth is that finding planets at astronomically vast distances is much more challenging than it seems. This task undoubtedly requires highly sensitive and highly specific telescopes. Not without reason, out of these over 5,000 worlds discovered outside the solar system, at least 3,000 of them are gas giants. These planets are quite large and consequently much easier to observe. On the other hand, we have nearly 2,000 worlds detected that resemble terrestrial planets. This category encompasses everything from common planets to those known as super-Earths, which have dimensions and masses greater than our planets. However, this does not guarantee in any way that these planets will have the suitable conditions to support any form of life. Based on our current understanding of how life formed here on Earth, only a few dozen of the planets identified so far are situated within the habitable zone of their stars. To find these worlds within the Milky Way, there are at least two more common methods. The first of them is radial velocity. This is very easy to comprehend and boils down to the planet's orbit with its parent star. Despite stars having substantial mass and strong gravity, the planet might have the ability to affect its motion in space. The telescope then records the variation in electromagnetic waves from the light emitted by this star. This variation will be caused by the gravitational influences exerted by the exoplanet as it orbits around the center of mass of the system. The star, in turn, moves back and forth relative to Earth, generating a known effect called a double shift, which physically manifests in the spectrum obtained from the star. The second method, which is even more common, is used for the detection of exoplanets and is known as the transit method. This method is comparable to a solar eclipse here on Earth, where the moon passes in front of the sun and its light is momentarily blocked. From the perspective of Earth, when an exoplanet crosses in front of its host star, there is a brief decrease in the brightness of the star. Telescopes are capable of recording these subtle variations in luminosity. If the exoplanet is in a relatively close orbit to the star, the transit may occur more than once in a short period of time, contributing to the confirmation of the exoplanet. This method has provided a significant portion of exoplanet discovery so far and continues to be an essential tool in the search for distant worlds. According to NASA's tally up to the day I am recording this video, 75% of the exoplanets discovered up to now have been through the transit method, 19% through the radial velocity method, and another 6% through various methods such as imaging and gravitational microlensing. But here, all exoplanets ultimately have something in common. They are all within the Milky Way. However, this could change with M51-ULS-1B. The scarcity of discovering worlds beyond the Milky Way is due to the vast distances involved. After all, the farther we go, the less practical resolution telescopes can achieve in distinguishing unique objects. To find a planet, the telescope needs to track the star, and in the midst of a galaxy millions of light-years away, the feat becomes even more challenging. M51-ULS-1B is named so because it was discovered in the M51 Galaxy within a binary system, the LS1, and it is the first find there. M51, also known as the Whirlpool Galaxy, was located 28 million light-years away. One of its main features is the visible gravitational interaction with its satellite galaxy, NGC 5195. The M51-ULS-1B was found in the main disk, more precisely in a peculiar system that seems to consist of a potential small black hole orbiting a conventional star. Astronomers are aware that vast distances pose a true challenge, and the system was carefully chosen to attempt to obtain X-ray data instead of the standard observations we obtain here in the Milky Way. In other words, astronomers utilized another part of the electromagnetic spectrum to locate this particular planet. In their research, around 200 extragalactic systems were considered, but only one exoplanet was found throughout the search. Despite the evident efficacy of the radial velocity and transit methods, they only apply to planets at a distance of approximately 3,000 light-years from Earth. This range is still within the far reaches of our galaxy, which spans about 100,000 light-years in diameter. Thus, in the pursuit of tracking the first extragalactic exoplanet, the idea was to seek planets that transit in X-ray binary systems, like the case of ULS-1 in M51. These systems contain white dwarfs, neutron stars, or black holes that gravitationally pull matter from their companion stars. As this material is dragged towards the black hole, the surroundings become intensely heated, generating powerful X-ray emissions. Unlike the optical transits we observe here in the Milky Way, in these binary systems, the X-ray emission region has a very concentrated range. Even a small planet can obscure a significant portion of radiation. This results in the detection of X-ray transits at much greater distances than visible light transits. In the case of the M51-ULS-1 system, a black hole or a neutron star orbits a star about 20 times more massive than the Sun. This causes the system to be one of the brightest X-ray binaries in the M51 region. Analyzing data from the Chandra Observatory, researchers noticed a sudden drop in X-ray emissions from the system over a period of 3 hours. This observation led researchers to conclude that something passed in front of the line of sight to Earth, indicating a potential exoplanet. It likely has the size of Saturn and orbits at a distance approximately 19 times that between Earth and the Sun. If confirmed one day, this would be the first planet found outside our galaxy. However, there's a somber note. This candidate won't return for another transit for over 70 years. The significant question that arises is, if there are so many planets within the Milky Way, why would stars in other galaxies be fundamentally different? The truth is that the universe is likely teeming with planets, each with its own possibilities. If you're eager to continue delving into the captivating mysteries of the universe and stay up to date with the latest astronomical discoveries, be sure to subscribe to our channel. Together, we will keep unraveling the secrets of the cosmos and expanding the horizons of knowledge. Don't miss the chance to be part of this incredible journey through space. Subscribe now and let's explore the universe together.